Okay, as the first example, we take the following function. We take a function which is defined on almost everywhere in 0 to infinity, but with one point missing. Okay, we just remove 1 from this interval, and so we have a function which is not defined in 1. And so this should be the adherent point that we are considering then. And the following function, f of x, is the square root of x minus 1 divided by x minus 1. Okay, so this function is obviously not defined in 1 because you cannot divide by 0. So 0 does not have a multiplicative inverse to be fancy, but we cannot divide by 0. So what do we do with this? I claim that this can indeed be continuously extended, and to do this, often the idea, what you really do in computations, and what you also see in exercises at some points, all you need to do at some point is to reformulate this function and give it another way of describing it, which is then defined in 1, which could then really even defined in the value of x equal to 1, and this is what we're doing right here. Namely, if x is not 1, we do the following computation. If we take a close look at square root of x minus 1 divided by x minus 1, some of you might have already seen the solution here, or the approach that works. Namely, this we can interpret as the third binomial formula, as the Germans call it. So this is the same as square root of x minus 1 divided by square root of x minus 1 times square root of x plus 1. So this is just this third binomial formula. Now, it's obvious what we can do. We can just cancel this from the fraction, and so we get that this is 1 over square root of x plus 1. And now our problem has disappeared. This thing is indeed defined in 1. There's no problem with defining this expression in 1. So we can just define a function like this. Namely, g is now a function on the whole non-negative numbers, so from 0 to plus infinity to r. G of x is 1 over square root of x plus 1. This is continuous. So well defined, of course, but this is continuous with g of x is f of x for all x which are not equal to 1. So this means we have found our limit. Namely, this shows the limit of x going to 1 of square root of x minus 1 divided by x minus 1. This is now, by definition, simply the value of the extension at 1. So this is g of 1, which is 1 over square root of 1 plus 1, and this is obviously 1/2. So this is the limit of our function in the point, right? So this is just a nice, clean example. Another example, which is maybe not that obvious, but where we also can see that we do a similar trick, but the trick that we need to make it visible that we can define it in 1 is a bit more tricky. So assume we have some number n, and we take the following function. We take fn, which is defined everywhere but not in 0, to r, and fn of x we shall define as 1 plus x to the power of n minus 1 divided by x. This is obviously not defined in 0. So what do we do with this? I claim that the limit also in this case exists, and this we need to, for this we again need to reformulate this in a nice way. So for this expression here, 1 plus x to the power of n, we have the binomial theorem, which makes precisely statements about kind of powers of sums of two elements. And so here by the binomial theorem, so what does the binomial theorem say for this expression? 1 plus x to the power of n. This is now equal to the sum from 0 to n, and now we have the binomial coefficient n over k. And now we would have n to the power of 1 to the power of n minus k, which is irrelevant because the powers of 1 are 1. So all that remains here is x to the power of k. So we now express this a bit, we expand the sum a bit, namely we take the first summand out of there, namely k equal to 0. We have seen by definition that n over 0 is 1. This is the way it is defined when here's a 0 below in there, and x to the power of 0 is also 1. So the first summand here is just 1, and the rest we leave as it is. This is n over k times x to the power of k. Okay, this is helpful because we can now see that's the way the function is defined. We subtract 1 and then do something interesting with the rest. And yeah, this means that here 1 is here explicitly a summand, so we just get as a remainder this sum here. This contains only powers of x where the exponent is 1 or bigger, and so dividing by x still gives something nicely well-defined, some polynomial. And this is now the way we can find our limit. And so now we're almost there already, actually, because this means that by definition, fn of x is the same as 1 over x times the sum k from 1 to n over k x to the power of k. If we just now multiply this out, so we take distributivity, this is the same as the sum k from 1 to n over k x to the power of k minus 1. So, okay, to make this a polynomial, a bit cleaner, we do an index shift. Namely, we just modify this k here a bit. This is an index shift. Namely, instead of going from 1 to n, we just change the summation to go from, so here we go from 1 to n, and so here we actually start at the exponent 0 and end at the exponent n minus 1. So we change this by going from 0 to n minus 1 in the sum and having an x to the power of k. And now we just have to think what needs to happen here. So here the k, this is actually 1 bigger than here because we kind of subtracted 1 from the whole index. So here we need to replace k by k plus 1 to get the original version back. So this is a polynomial. This expression holds. And now we can define the polynomial on R. So g, which is now mapped from R to R, which is just this polynomial expression. G of x is the sum from 0 to n minus 1, n over k plus 1, x to the power of k, is a polynomial. And we've seen polynomials are continuous. Continuous with g of x equal to f of x for all x not equal to 0. So this shows that we have our limit. Namely, this shows that the limit of x going to 0 of 1 plus x to the power of n minus 1 divided by x, that this is now the same. Oh, sorry, this depends, of course, on n. So let's also give this the index gn. If this is fn, let's call this gn. And here we have also n's missing. Sorry about that. So this is now the same as gn of 0, because we go to 0 in this situation. And if we have a polynomial, of course, if we take 0 as the variable, the only thing that's remaining is the constant term, so the term with exponent 0. And this is simply n over 1. And if you don't recall this, this is something you can just write down. This is n factorial divided by 1 factorial, which is just 1, divided by, multiplied with n minus 1 factorial. And all that remains here is n. So this here converges to n. Right? It's actually, the theory behind this looks quite complicated, and everything in this section looks complicated because of all the bookkeeping and all the continuities there and so on, but the computations that you get from this, and that you also see in the exercises, they are actually not that hard, I would say. So I think this, also some reasoning like this should be familiar from high school for you. So I hope at least, so you might be, this might be a convenient topic, I think. Okay, first of all, another characterization of limits, and this is now basically a justification for the notation here, because I've defined this, I'm using the notation limit of x going to a, but this is kind of, so far I've just defined this as the value of a function and I'm not taking any limits in terms of sequences or something. So why can I call this a limit? And the reason for this to be called a limit is basically because it is indeed connected to sequences. So let's say we have some domain D, we have an adherent point of D, and we have a function on D which is continuous, and assume we have some value in C which is given, which should be our limit then. So L in C, which is a fixed value. If we have this, then the limit of x going to a of f of x is L if and only if, and now we can characterize it via sequences. For each sequence xn in the domain, so this sequence in D, which converges to our point A that we want to study, so with limit n to infinity xn equal to A, we want that the values of the image of the sequence under F converges to L. So it holds that limit n to infinity of f of xn is equal to L. So this kind of justifies this limit notation. And actually this does not need to be proven because we've already seen this. This is defined in terms of a continuous extension, and this is simply sequential continuity for the extension, if we would write this down in detail. So this is actually, this follows basically directly, and so I will not really give a detailed proof. I just write as a proof, we apply Theorem 3.3, which was the sequential continuity criterion, to the continuous extension. Continuous extension of f, and similarly for the sequential continuity was an equivalence, which basically says that kind of some extension is continuous. If we do this like this, if the sequence thing holds, so this direction here, this is all contained in the sequential continuity property. Okay, so this is kind of why we call this a limit. This has some advantages, because now we can just also use our computational rules for limits. If you recall the sequential continuity theorem, once we had this, we could just, we had some nice rules for continuous functions. We had nice computational rules then. And so basically we could use this nicely, and this is the same that we can do now to use some nice properties of the limits with respect to sums, products, and so on, that they really behave well. And this is something I will now do in the next theorem. Okay, I will now summarize several properties of limits of continuous functions, and they basically follow from the analogous properties of continuous functions themselves, because we have seen that sums and so on, so the continuity of them we've always shown using sequential continuity, and you can basically do the same here. So I will not give a detailed proof, because actually we've already shown this, up to some minor details which might be interesting, but we will skip them. So, Theorem 350. We have, again, a domain in C. We have an adherent point. And we have a function, we have two functions, f, g, from D to C. And we assume that they both have a limit in A. So the value might be different, but they have value in A. Then f plus g, the sum, has a limit in A. And it holds that the limit of the sum is the sum of the limits here as well. So limit of x to A of f plus g of x is the same as limit of x to A f of x plus the limit of x to A g of x. Okay, so keep in mind f and g do not have to be continuous or something. We just assume that they have a limit in this point A. But this basically the proof would be then the same as showing this for continuity in A. Okay, this looks like I was drunk, but I am not. Okay, sorry. Secondly, so sums, now you can guess what I'm doing next. F times g, the product, also has a limit in A, and it holds that this limit behaves well with respect to products as well. F times g of x, the limit in A, is the product of the two limits. So limit of x going to A of f of x times limit of x going to A g of x. Okay, third case, quotients. Here I need to be a bit, I'm a bit sloppy because I will not explain this in detail. So in general, first of all, if you take a quotient of f divided by g, the first thing we need is that the limit of g is non-zero, otherwise we don't need to talk about this. If the limit of x going to A of g of x is non-zero, and then you can show and this is something I will not do, but yeah, there exists a D bar neighborhood of A, so some nice points around A. This is so some points sufficiently close to A contained in D, they have this property. So there exists some D bar neighborhood A of small a, such that G does not vanish on this neighborhood. So with G of x is not equal to 0 for all x in A intersected with D. And there we can now define the quotient. And f divided by G is now defined on A intersected with D to C. So this function is now well defined. This has a limit in A, and also the nice computational rule holds with the limit of x going to A f divided by G of x is then the quotient of the two limits of f and g. So limit of x going to A f of x divided by limit x going to A g of x. I don't know about you, but I always find such formulas quite satisfying, because here we can now see that at least studying math in the first term is incredibly hard and it's very complicated. Everything looks so wild, but here there's now something which makes sense. So limits commute with these operations and so on, and something behaves as we would expect. So sometimes this is kind of a relief that kind of somehow mathematics is not completely breaking down as the math we knew. So this is really useful for computing limits in practice. So we can just use these things then if everything behaves well. And here, as I said, I will not really go into detail because we need kind of basically sequential continuity, or in other words, the theorem I had before. So this sequence criterion for limits, and then basically the same thing we did for continuous functions. So basically, we apply theorem 349, proof in analogy with this theorem that had the properties of continuous functions, and this is theorem 3.5. Okay, and I will not go into detail on this, but we can use these things. Okay, now this is nice computational rules, and you will kind of have opportunity to use them in the exercises. But now I will proceed with a bit more theory. Namely, I will now introduce another criterion for limits, which is actually for computations not really helpful, but this gives us the opportunity to show something really nicely. Okay, we say we have a domain, we have an adherent point of the domain D, and we have a continuous function on D. So this time we assume that f itself is continuous. So in this case we have a nice description of the limit, namely then f has a limit in A if and only if for all epsilon bigger than 0 there exists some delta bigger than 0 such that f of x minus f of y is smaller than epsilon for all x and y in a neighborhood of A intersected with D. So B delta of A intersected with D. Okay, this might look familiar if you think back about an hour or something. Namely, this looks similar to the definition of uniform continuity. Here, basically, the only difference is that A does not need to lie in the domain of D. So this might actually, so this is only difference, but here we can just formulate this very analogous to uniform continuity, and we shall see that this is then helpful here in this case. But this is now the condition here, and if you take a look at this condition, this has one big advantage. Namely, we don't need to name a limit. Here we can just show the existence of a limit without having a candidate. So with the other criterion, so with continuous extension and so on, you kind of need to guess a limit, so to find this some way, and to compute that you have that this has this property. But here we only need to know f, and we don't need to study the limit, and we don't need to have a candidate for the limit. So this is the nice thing about this, and this is why it's kind of useful to prove theorems sometimes. Okay, let's prove this. So first this direction, so we assume we have a limit. So we have a continuous extension then. So let G from D united with A to C be a continuous extension. Extension of F. Okay, now we need to show for all epsilon blah blah blah. So we take some epsilon bigger than 0 and show that we can find some delta with this property. So G is continuous. Hence, there exists, so G is now defined in A, that's the difference here. So there exists some delta bigger than 0 with G of x minus G of A, so we have continuity in A that we use here. And this is smaller than epsilon over 2, yes, one of these proofs again. Smaller than epsilon over 2 for all x in B delta around A intersected with D, the union with A. This looks more complicated than it is. So this is now, we have this delta, but then this delta has a nice property, namely, to compare this with to G and F. I mean, G and F are really related. As soon as we are not in A, G is F. So this particularly means that f of x minus f of A is smaller than epsilon over 2 for all x in B delta of A intersected with D, simply since G coincides with F in there. And now we can use the triangle inequality and we're almost done. Namely, now it follows that f of x minus f of y for any 2 points x and y in this delta disk, that this is smaller than, or this is first, I read this is the same as f of x minus f of A plus f of A minus f of y, and now we can use the triangle inequality. And we just flip the order of these terms by adding an additional minus sign, which is not important here. This is smaller than or equal to f of x minus f of A to the absolute value plus f of y minus f of A to the absolute value. This is smaller than epsilon over 2 plus epsilon over 2, which is epsilon. And this holds for all x and y in B delta of A intersected with D. And this is really the condition that we wanted to have. So this proves the one direction. Okay, for the other direction I need quite some space, so let me just erase. For the other direction, so we assume this epsilon delta property and we want to show that the limit then exists. And for this I want to use the sequential criterion, so this continuity of sequences that I had before in this theorem. So we start with some sequence xn, n and n. This is a sequence in D, which converges to our point A, so with limit n to infinity xn equal to A. Okay, now we use epsilon and deltas. So we have, by assumption, epsilon bigger than 0 and a suitable delta bigger than 0 such that f of x minus f of y to the absolute value is smaller than epsilon for all x and y in B delta of A intersected with D. To repeat this, this was the assumption here basically. So here, this sounds a bit sloppy. For epsilon bigger than 0, we take a suitable delta, just to be precise. So given with respect to epsilon, but we can find this, such that this holds. So on the other hand, we know that xn, n and n, converges to A. So in particular, for this choice of delta, we know that at some point the sequence will be inside this open delta disk. This is convergence of delta. So there exists an n0 in n such that xn minus A is smaller than delta for each n bigger than n0 or equal to n0. And this is then now in our new notation. This means xn in B delta of A for all n bigger than or equal to n0. Okay, what does this mean? Well, how does this help us? This now gives us, if we are if n is bigger than or equal to n0, we're in this area. So if x and y are both terms of the sequence which have large enough index, we get that this is satisfied. So this means f of xn minus f of xm, if we just take two terms of the sequences, and we assume that they are both beyond this threshold n0. This means that this is smaller than epsilon for all m and n bigger than or equal to n0. This looks familiar. Namely, this is the condition that we've seen before. This means, because epsilon was arbitrary, that the sequence of f of xn, n and n, is a Cauchy sequence. This is just this definition of a Cauchy sequence. And we've seen, this was theorem, corollary. Yeah, in the complex, the real case was the theorem, the complex case a corollary. It follows that f of xn, n and n converges. Okay, so let's give this limit a name. Put b to be the limit of n to infinity f of xn. Okay, now, what's now the problem? Why aren't we done yet? Because we wanted to show that the limit of this converges to this value. So if I would have an audience now, again, I would ask, what's the problem here? The problem is we don't know that for each sequence that this value of b is the same. So if we take another sequence, it might have a different limit. So this is a priori not clear. So what's happening if we take a different sequence? So by the same argument, we could then still get that we get the convergence of this f of xn. So what's happening? So let's take another such sequence. So if xn prime, n and n, is another such sequence, we define a third sequence, which is now called yn, n, and n, and just informally written at this infinite list, we just take as the terms of y, we take alternatingly the terms of x and x prime. Namely, we first take x1, then x1 prime, then x2, then x2 prime, and so on and so on. So formally, yn is either xk if n is 2k minus 1, or it's xk prime if n is 2k, and this for all k and n. So we've got for all odd and even numbers, we have these two definitions, and so we get a sequence. Okay, then, it's something that I won't prove because it's kind of quite easy to see. So another such sequence, I mean that this also converges to A. So then we get, with a little computation, which is actually not too hard, that yn converges to A as well. So this is also a sequence converging to L. Can show as above, so doing this same Cauchy argument and so on, that f of yn also converges. Okay, so what does this help? This has a nice consequence, because these two sequences, xn and x prime, they are both subsequences. The one is taken if we just take the odd indices, the other if we take the even indices. So since xn, n and n, and xn prime, n and n, are both subsequences of f's. One mistake I made. So I would, of course, for the same goes for f. So if f of yn, we get the two subsequences f of xn and f of xn prime. Since f of xn and f of xn prime, this now looks terrible, but anyway, are both subsequences of this sequence here. Now we're good, because we know that this sequence converges, so all the subsequences converge against the same limit. So this shows that the limit n to infinity f of xn prime, this must coincide with the limit of f of yn, and now vice versa. this is the same as the limit into infinity of f of xn. And this is what we call b. So they indeed go to the same limit. So this has the same value. So this value of b, this limit of one sequence is the sequence of one such sequence is the limit of every such sequence. So this shows we have a limit. So this shows by theorem 349, which was the sequential criterion for limits, that then limit x going to a of f of x is precisely this value b. And this shows that especially that we have such a limit. Okay, so this proves the result. Now, this is a criterion which is very technical and theoretical. So what is it good for? This is, as I said before, this looks a lot like uniform continuity. And this is now its most useful consequence that will actually be needed in some situations. So corollary 352. Okay, we have again d subset of c, and we have this time a function of d which is uniformly continuous. Actually, I should have worn a uniform today, but okay, uniformly continuous. Then it follows that there exists a continuous extension to every adherent point. This means to the whole closure of D. So a continuous extension G defined on the closure of D to C of F. So whenever we have uniform continuity, we have all limits. So all the limits exist. This is what this kind of gives. This is what this helps us with. And this is really beautiful because many functions are nice and uniformly continuous. So this is the useful property. So what do we need to do? We take some adherent point, we call A, and we just need to show we have we have an extension to A, and then of course we have an extension to every point, since this is arbitrary. So, and epsilon bigger than 0. Okay, then just a little computation now. Then there exists, since by uniform continuity, we have a delta such that f of x minus f of epsilon to the absolute value is smaller than epsilon for all x and y in D with, and now I make a little computational trick with x minus y smaller than 2 delta. Of course, if I can find a delta, I can just divide it by 2 and take a new delta which has this nice property. So if this holds, then now here's the problem because we can't formulate this for A because A does not need to be inside of D. But this implies that if we take x and y in the delta ball, open delta disk around A, there we get that x minus y to the absolute value. And now we can use the triangle inequality again to estimate this by x minus a plus y minus a to the absolute values, and by just subtracting and adding a here and playing with the signs. So we get this. So this is now smaller than, so these are in the delta balls of A, so this is smaller than delta plus delta, which is 2 delta, and now you see why it shows it like this. Since this holds, it follows that f of x minus f of y to the absolute value is smaller than epsilon for all x and y in B delta of A intersected with D. And this shows the claim because this is now the theorem I just proved. So this is now a theorem, 351. F has a limit in A. Since epsilon was arbitrary and we found a suitable delta, and so on. Okay, so we have an arbitrary adherent point, so we can, in every point we can find this extension, and this is what we wanted to show. Okay, so uniformly continuous functions are nice. That's because the first beautiful property of uniformly continuous functions. Okay, Next, we want to focus on a slightly different setting. Namely, we want to focus on limits of functions defined on subsets of R. So, for example, intervals and so on. So, for those of you who still not feel too familiar with the complex world, we are now getting real again. And yeah, we will see that there we have some special things we can only define in the real case, like left-sided and right-sided limits, as we shall see next. And there we will see some more examples and interesting behaviors. See you then.